Natural power has been the heritage of mankind since the earth was created. To man was left the adaptation of this power so that it could be harnessed to industry. Prehistoric inhabitants of the world must have stood in awe before huge waterfalls or crouched in fear in their caves as the wind whistled and shrieked overhead, little dreaming of the vast resources hidden therein. Through the ages, this initial wonderment has given place to curiosity, familiarity, and finally adaptation. With years of evolution came the windmill and the water wheel, both of which have dotted the countryside since the earliest days. While the use of wind has steadily decreased, water power has been developed to a very high degree, some of the largest electric supply stations in the world being driven by natural power. It was soon realized, however, that while admitting the efficiency of water and wind, they were also locally controlled, and that what was needed was a mobile unit generating its own power. Thus came the introduction of the internal combustion engine, the foundation of the automobile industry. With numerous components working at high speeds, it calls for a great degree of efficiency in manufacture to generate a predetermined power and to be able to run for long periods on a small fuel consumption. Let us briefly describe the methods which are used to produce the famous Morris engines. Our engine is composed of three types of components, that is, those made by casting, where huge quantities of metal are melted down in cupolas and then poured into molds of the required shape. Those made by forging, where the metal ingot is made red hot and hammered to shape between steel dies. And finally, those turned direct from bar metal, which is produced by taking huge ingots of white-hot metal and reducing them through rollers to the diameter required. And now let's see the actual manufacture of several of the larger components. Here, a red-hot crankshaft forging is having the surplus metal removed in a trimming press. It is then placed in a circular jig, firmly clamped into position, and the journals and end flanges rough-turned. In the same way, but located off the already turned journals, the crank pins themselves are machined with an allowance left for grinding. Transferred to a turret lathe, the flange and end are finished turned to length, and the seating for the flywheel bearing recessed. The pins and journals are now rough ground. The oil passages for the high-pressure lubrication system are drilled with the aid of inclined spindles. This is an operation requiring a very delicate touch. The drills being long and fragile, great care is needed lest they should break in the hole. Finally, the crank pins are finished ground. Most gears have their origin in steel forgings, and here you see an assorted collection of blanks. The first operations on these are invariably done on a semi-automatic turret lathe in which the tools are automatically brought into position. Here a bore is being drilled while tools on cross saddles turn the front and side faces. In the case of gears which have extra long bearings, such as in the case of this lay shaft, they are drilled on a machine equipped with a rotating jig. Drilling, however, does not ensure a parallel hole, and in order to correct this, broaching is resorted to. This type of machining is accomplished by using a tool which has annular cutting teeth smaller than the desired diameter at one end, increasing with a gradual taper up to the maximum size. This is pulled through after the hole has been drilled. After turning the body, the teeth have to be cut and ordinary spur gears are produced like this. The cutter moves up and down while the gear blank rotates round it. Spiral gears are cut on a hobbing machine where the cutter rotates and travels along according to the pitch. To assist you in gear changing, the ends of the teeth are rounded. The gears are now passed through a hardening process and the remaining operations completed by grinding. This particular one is mounted in a jig which locates the gear on the teeth, and a grinding wheel traverses the face, being automatically followed by a smaller wheel which sizes up the bore. Gears with long center bearings are mounted on a machine like this and the hole ground from both ends simultaneously. Now, in order to ensure a perfectly smooth face to the teeth, gears are mounted between 3 cast iron wheels of a similar pitch, loaded with an abrasive paste and passed backwards and forwards, while periodically their direction of rotation is reversed. This is known as lapping. Yet another example of forging is that very vital part of an engine, the connecting rod. These rough forgings are clamped firmly in a milling jig, and 8 faces, 4 on each, are machined at once. In this operation, where steel is cutting steel, large quantities of oil have to be used, otherwise the tools would soon become very hot and lose their edge. This is also a very good instance of speed in production, for while one pair of rods is being machined, the other side of the fixture is being loaded with fresh forgings. Having obtained 2 parallel faces and locating off the contour of the ends, we can now drill and ream the small end, that is the gudgeon pin bearing. The natural sequence is to locate from this hole and core drill the large end, that is the end which will ultimately become the crankshaft pin bearing. The big end cap bolt holes are drilled and reamed in duplicate jigs like this, very nearly as fast as the operator can load them. The rod is now clamped on a horizontal milling machine and the top half bearing parted from the arm. Here again a continuous loading type of jig is adopted. The white metal lining is next cast onto the steel bearings, the complete assembly placed on the faceplate of a turret lathe and very accurately bored to size. Very fine limits are worked to here in order to ensure the finest possible surface for the crankshaft bearing. However, not satisfied with this boring, a further operation is carried out by rolling, the basis of which is that a cage containing hardened steel rollers of a dead accurate overall size is forced through the bearing, thus giving a very highly burnished skin to the surface. Another type of component is a casting, such as a cylinder block. Castings are produced by pouring molten metal into molds and allowing it to cool. When this has been done, the molds are broken away and the solid metal remains. These castings are cleaned up with the aid of pneumatic chisels and portable grindstones. The block is then securely fastened on huge milling machines and is passed under powerful cutters which remove quite a quantity of metal in their slow progress. A cylinder block naturally has a large number of holes in various parts, and these are drilled with gangs operating simultaneously, such as this. Tapping is also done en masse, but here care has to be taken owing to the fact that several of the holes are blind, and if the taps were not stopped in time, they would be broken. The bearings for the crankshaft and camshaft are machined with the aid of long boring rods and shell reamers. And now we come to a most important part, namely the cylinders. These are all bored to very fine limits at one operation like this, and in order to give a beautiful smooth finish with a lasting surface, they are afterwards rolled on a machine of a similar type. Another type of casting is that made with the aid of dies, and is used in producing pistons. In this case, the dies are hollow and the metal is forced into them under pressure, which gives a very clean casting and reduces machining to a minimum. The first operation is to turn and bore the skirt. The next is to rough bore and ream the very important gudgeon pin hole, which is accomplished on this rather weird-looking machine. The pistons are loaded at the top, and 2 pairs of tools operate in alternate sequence on them at the bottom of the circle. The outside diameter and the piston ring grooves are next turned on a semi-automatic lathe. The series of oil holes in the circumference are accomplished simultaneously with the aid of motor-driven drills mounted in a circle around the piston. The pistons are now placed in this strange-looking machine, and the gudgeon pin holes are finally bored with a diamond cutter. They are then transferred to what is called a shaving lathe, and two tools are brought into operation, one of hardened steel, which operates at the back, while in the front is mounted an actual diamond, which not only takes off a very fine cut, but also imparts an extremely high degree of polish. The utilization of diamonds in the cutting of metals is one of the latest advances of engineering science. The reflections in this piston show how well the diamond does its work. Many tons of steel bars are used in the production of components which are turned from them direct. Here, for instance, is a camshaft being rough turned, but in order to relieve the cutting strain on the machine, only half is turned at a time. It is later transferred to another automatic machine on which the cam faces are rough turned. The tools are operated by means of a master camshaft, which you can see at the top, and the cams themselves can be seen taking shape on the shaft at the bottom of the picture. The small gear operating the oil pump is next cut with the aid of a hubbing machine. And finally, after hardening, the cams are ground dead accurate on an automatic machine, which grinds them with the aid of a master camshaft and feeds the shaft along to each successive cam. Gudgeon pins are another example of bar work, and after being parted off to length, are placed in this hopper, which is attached to an automatic lathe from which the pins are fed into the chuck as required and the center hole drilled. After this, they are externally ground on a centerless grinder. This machine passes them between large grinding wheels into which they are fed by means of a chute. Being able to dispense with centers, this is a very speedy operation, and they are shot out onto this chute almost as quickly as shelling peas. Accurate as this method is, the standard of Morris Motors Limited is even higher, and they are submitted to a further operation known as lapping. For this operation, they are placed in a wooden guide, under and in contact with which is a large wheel of very fine abrasive. As soon as the machine is fully loaded, another wheel is lowered into contact with them. These wheels are then rotated at high speed, the ultimate result being a dead accurate diameter with a very high degree of polish. Of course, hundreds of small components, such as nuts, bolts, screws and pins, are produced entirely with the aid of automatic machines such as this. Here you see a cheese-headed screw being made complete without the aid of human hands. The bar of metal is first fed up to a stop, where a turret containing several tools automatically reduces it to the required diameter and then cuts the thread on the end. When this is complete, an arm, which is almost human, swings across, taking hold of the screw, while a cutter at the back moves over and parts it off to length. Swinging back into position with the screw in its grip, it holds it firmly, while a small circular mill advances and cuts the screwdriver slot. Immediately this is complete, the screw is ejected and the operations are continued until the length of bar is exhausted. And thus, in an unceasing stream, these odd-shaped pieces of raw material pass through the huge Morris machine shops, gaining shape en route until finally they are passed off as finished components worthy of their place in whatever engine, large or small, that they are destined for. And by various methods, chute, lorry or conveyor, they find their way to the engine assembly shops. Here, rows of highly skilled mechanics are ranged alongside a runway, down which the engine passes and gradually takes shape. At regular intervals, batches of components arrive at the correct position, and as each man assembles his part, the engine passes on to the next. These lines are really the vindication of the Morris system of specialized testing. Each part, accurately produced to within very fine limits, fits easily and without any force into its correct location. Crankshaft and pistons, camshaft, flywheel, clutch and valves all go together like some child's jigsaw puzzle. And finally, the cylinder head is lowered on and bolted into position. And so we have a complete engine. The only thing remaining is to ensure that it shall be up to Morris standard. This is ascertained by securely bolting it to a test bed, on which it is first driven by electric motors to free it off, and then under its own power. Here, test figures can be obtained, which give an accurate forecast of its performance. All engines which do not attain a predetermined degree of efficiency are rejected, so that only the very best are built into the car, which, whether you are traveling through the busy cities or quietly touring the beautiful countryside, will inspire you with confidence and serve you as only Morris can.
This is the train, which if the experiments prove successful is going to make travelling very much cheaper for all of us. The invention of a young Irish electrical engineer, it is driven by power from accumulators which it carries. When the train comes to a standstill at the station, recharging of the batteries commences automatically by the contact made by the shoes fitted to the roof of the coach, which you can see here. Here's Dr. Drum, the inventor, telling President Cosgrave all about it, before they set out on a trial run with most of the Irish Free State ministers as passengers. On the trip from Westland Row to Bray, everybody was amazed at the rapid acceleration. The top speed will be about 60 miles an hour. Whilst this wonderful new advance in electrification of the railways is still in the experimental stage, it really does look as though in the near future we shall be able to pop down to the seaside or up to town to the pictures for a few pence instead of pounds.